what I should be doing here for this formula, kind of jumping ahead of myself. Um, we've had frequency distributions where you've got your class and you've got your frequency in this column. So the class would have been something like, I'm gonna just make it easy on myself, 0 to 1, 2 to 3, 4 to 5. And then your frequencies would have been, I don't know, some number. So just to put this into context, maybe the class would have been, say, the number of, let's say, the number of coins that somebody carries in their pocket. So you had 5 people that carried 0 to 1 coins. Let's say we had 2 people that carried 2 to 3 coins, and you've got 1 person that had 4 to 5 coins. So when you got a frequency distribution, that's where this mean formula is going to come in. The x in this formula is not actually listed here. So the x is the midpoint of each class. So for example, to get the midpoint of the first class, you'd get, or what you'd do is maybe create another table where this is the midpoint. So you'd say, take the upper class limit and the lower class limit, add them together, and divide by 2. Well, of course, that's 0.5. And so the next one would be, the midpoint would be 2.5. The next one, the midpoint would be 4.5. But the frequencies are there. And so what you end up doing with this formula is you multiply the frequency times the midpoint. So on top, you'll have frequency times the midpoint plus the next frequency times the midpoint plus the next frequency times the midpoint. So however many there are, and then you divide all that by the sum of all the frequencies. Crossed out my 1. So this will just be on the bottom is 5 plus 2 plus 1. All right, so the other mean formula, the first one we saw, that was x bar equals sum of x over n. And that's just what you usually think of as the mean, where you might have a bunch of data. So like, I don't know, just make something up really quick. 5, 3, 9, 1. And so if you had to find the mean of that data, this formula is just saying, add the data up. So 5 plus 3 plus 9 plus 1, and then divide it by the number of data that you have. Does that make sense? So if you're trying to juxtapose those, that's kind of the big difference. One of them is the mean for a frequency distribution. The other one is a mean for just a set of data. So now, going back to what I originally accidentally was mentioning, let me look at the formula sheet again. If we go way down here, you've got this mean, and then let's see, I think you got this mean also. So let me talk about when to use those formulas. So we'll try to keep everything grouped like that. The means, there's just different situations. So the mean across this, the formula where it's mean equals the sum of x times px. That's what I started out talking about. This is where instead of a frequency distribution, you've got that discrete probability distribution. And that was where you've got x, you've got px, And now I think I had picked 0, 1, and 2 in this column, but it could be anything. And then in this column, I was making up some probabilities, 0.5, 0.2. And so to use this formula to calculate the mean of a probability distribution, I'll just point out this is probability distribution. What you do is you take, for each x, you take that x and you multiply it times its probability, and then the sigma tells you to add them all together. So you just take 0, 0.3 plus 1 times 0.5 plus 2 times 0.2, and then you figure out what that is, and that'll be your mean of your probability distribution. All right, so we've got those three means. What that last one is, where it says mean equals n times p, that's kind of the same idea as the last one. But this is specifically if you know that you're dealing with a binomial situation and you want to calculate the mean of the probability distribution. Binomial. So the idea here is, in a binomial situation, it meets several criteria, that there's a fixed number of trials. Each trial has two possible outcomes that we call a success and a failure. The probability of success on each trial stays the same, and those trials are independent. That tells you you're in a binomial situation. And so you end up with some n, let's say 10 trials. You're given some probability of success like 0.7, 70% chance of success. And so what you could do is you could build out the probability distribution. So since there's 10 trials, that means I'm going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the hard way to calculate the mean in these situations. So don't do this, but just to kind of put it in perspective, I'm going to show you what's really going on. And then for each of these probabilities, you could use, so let's pick on 4, probability of 4. You could use the binomial distribution formula, probability formula. So I'll show you that on the formula sheet. That is this one here. You could use that probability formula to calculate each of these probabilities. So if I'm just picking on 4 for a second, then that formula would say, all right, do 10 factorial times, or divided rather by 10 minus 4 factorial times 4 factorial times the probability of success to the 4th times the probability of failure, which is just 1 minus the probability of success. So these two always need to add up to 1. 1. And then this, actually, let me state where this comes from. That's the n minus the number of successes. And so this formula you could use to get all the different probabilities. These are question marks. This whole way through. And then if you wanted the mean, then you could go back up and use that formula that we just talked about, this x times px. But like I said, that's the hard way to do it. If you know that it's binomial, then the mean is just going to be the number of trials, which in this case is 10, times the probability of success. And so in this case, it'll come out to be 7. So in other words, this formula it's a shortcut way to calculate the mean if you know your probability situation is binomial. So stop me at any point if you guys have any questions. But if you're okay with those means, so those are the 4 different mean situations that we'll have on this exam. Okay. All right. Then let me jump back to the formula sheet and um, let's get into the standard deviation. There are, let's see, there are several different standard deviation formulas. Um, these two are equivalent. So I tend to just pick on one of them. What what they do, just like this mean formula, that was the way you calculate the mean of a set of data. If you want the standard deviation of that data, you can use either one of these formulas. So one of the nice things about this second formula is you don't have to first calculate the mean. So, I kind of call this a shortcut formula, even though it looks a little uglier, but it's not much of a shortcut. So if I were to go back up to my problems here, that standard deviation formula would be akin to this, where you just got some data and you need to calculate the standard deviation for that data. So let's see, do I have the mean? 8, 10. Let me get the mean here really quick. 18, that's going to be 4.5. So now if I want to calculate the standard deviation, symbol, I'm talking about S. What we do is for each of the data points, we want to take 5. So the 5 from my data minus the mean, which will be 4.5 squared, and then add to that the next one. So now go to 3 minus 4.5 squared. And then I'm running out of room here, but that will continue on for each of these. And then on the bottom, you just have to divide by the number of data that you have. So 4 in this case, but for standard deviation, we always subtract 1 from it. So that's what the formula means. I'm using the first formula, which is sigma x minus x bar squared over n minus 1. Okay, so like I was saying, this one is the same thing. It's equivalent. We just don't need the mean for this formula, but it'll get you the same answer. Okay, so that would also be used for data. Looking at these other standard deviation formulas, let me pick on this one. So both of these are ways of calculating standard deviation from a probability distribution. So like these two problems here, we could calculate the standard deviation of some probability distribution like this if we use either of those two formulas. So for example, if I wanted to, well, I guess it doesn't really matter in this case, because in both cases, for this standard deviation, you have to get the mean first. So we could pick on the first one, say, all right, that is just the square root of the sum of, and then in parentheses, we go an x, px squared minus mu squared. But we could just as easily have picked on the second formula. So either one works. And what I would say to do is pick one of the two formulas that makes sense to you and just do that one every time and ignore the other one completely. Because I'm never gonna ask you to use one over the other. So just pick which one makes sense to you and use it. So for example, on this one, the way it would look is you have your square root, and this, I bracketed this x squared times px in parentheses. And that is because that's the only thing you're adding up. So you're only going to subtract the mean squared one time. So, and I should maybe get the mean first. In this case, it's going to be 0.5, 0.4. This will be 0.9.
So the like, what is that thing called? That's like that weird E thing.
Yeah, this symbol that looks like this.
Yeah, what is that called?
It's called sigma, but you have to be careful because this is also called sigma.
Okay.
Okay.
They mean totally different things. It's kind of like these are Greek letters. And so it's kind of like how a capital A looks different from a lowercase a. That's what this is. But regardless of the name, what this one means is add stuff up.
Okay, so it kind of is kind of like a 0 or a nothing in the equation, but it's like
yeah, it's telling you what to do in the equation. It's not putting new numbers in. It's saying everything after this, add that stuff up.
Okay.
So like in this formula, it's saying this is saying add up everything that's in parentheses after the sigma.
okay.
Okay.
Okay. And then for those, so the three, my dog is going crazy.
Yeah.
Oh my gosh. On the right column, the third, fourth, and fifth one are all standard deviations, and that could be used for the bottom left mean. Is that what it is, or the top right one?
Okay. Yeah. So this one and this one.
Okay, not
the same. And so either one of those could be used to calculate the standard deviation of a probability distribution like this.
Okay. Okay.
But and then the other one we talked about, these two, those are just calculating standard deviation when you just have a list of data.
Right. Okay.
And then this one, it's basically, if you notice, it's the same thing as this, just without the square root, because it's been squared. And it's pointless for that reason, because it really doesn't do anything special for us. But we call it variance as opposed to standard deviation when it's like that. And we use variance in some equations, and we use standard deviation in other equations. But the way you calculate it is exactly the same. You just don't take the square root. Most of what we're going to do, though, involves the standard deviation.
Yeah.
So if you're ever asked to calculate variance, and there could be a question on the exam about that, then you're safe just calculating the standard deviation if that's what you're thinking of, and then squaring it to get rid of the square root, and you'll have variance. Okay. So this formula maybe doesn't even need to be on there because it's really just the stuff under the square root here. So it's kind of redundant, but could be asked. So in other words, these three formulas are all, may as well be the same thing.
Okay.
Just this one doesn't have the square root. So then this one is also for a probability distribution, but specifically for this binomial case where you know you're in a binomial situation. All you have to do there to calculate standard deviation is square root of n that you know, so that'll be the 10 here in this case, times p, which is given as 0.7 in my example, and then times q, which q is just 1 minus p. So q in this case will be 0.3.
Okay. Right. Okay, that makes sense.
Mm-hmm.
And then I also I have somewhere to be in, like, so we have to head out in like 15.
Okay. But do you want to just quickly run through what the rest of these are?
Sure.
Yeah, whatever.
Yeah. I
What
mean,
do you guys think would help?
I was also curious on like this is very helpful, but also like implementing it into all the word problems because of word like all the words just like jumble together and it's
Gotcha.
hard to differentiate like because a lot of the like even homework ones I would do it in like an equation and then it would be the wrong answer and then I would like check with my parents or whatever and then they'd be like, oh, it is actually a completely different equation. It like feels like it like they both work, and so it's hard to like figure out which one. And this is very helpful for that. Um, but I'm just wondering if we could go over like even like the first question on the review,
Sure.
see
Yeah,
what,
like this time it takes me to wash the dishes question.
yeah, or something like any of them. But
Okay. Yeah, we can. How much time did you say you have?
like 10 minutes.
Okay. All right. So yeah, maybe we can just pick a few and talk through how you could decide what type of problem it is. So for something like this, where it says it's uniformly distributed, that's your keyword right there. As opposed to let me find one really quick. Here, number 5 says they're normally distributed. So uniformly distributed and normally distributed are two opposite things. And so where it's uniformly distributed, if you remember, that's the type of problem that uses a rectangle to calculate probability.
Okay.
So whereas normally distributed, you're using the bell curve and either a spreadsheet to get the probabilities, or you could be using the normal distribution table that I posted to Canvas. So either one of those works. All right, so do you want to go through number 1, or you want to just kind of talk about anything?
What do you think?
I mean, I'm not too sure.
Okay, well, tell you, let me go ahead.
I was gonna say, what do you think would be like the most like helpful thing for us to like have down, or like I don't know,
For the
or, like
exam.
for the exam, or like
Well, I will tell you, I could have a uniform problem on there, but it's not the focus of the exam. Certainly, normal distribution will be more heavily represented because that's really kind of the more major distribution. So there would be at most one problem related to uniform distribution. So it'd be good to go over, but if you're short on time between now and when you take the exam, definitely focus more on some of these normal distribution problems.
okay.
As far as those two probability distribution types.
Mhm.
But yeah, other than that, I could maybe just look at some of these others and just kind of mention what you want to think about and kind of the type of problem it is. And that might help you kind of group and see what the wording is to help you see what type of problem or what formulas to use.
Mhm.
So like anytime it says normally distributed, that's your key that you're using a bell curve. You're going to be using that table of that normal distribution table. Something like number 3, though, it doesn't say anything about what type of distribution it is, but it does ask for a probability. So it may be helpful to spend a minute when you see that and say, do I know what type of distribution this is? If it's normal, it'll say normal. If it's uniform, it'll say uniform. But there could be just a general probability distribution, which would look just like I came up with here. So this is what I would call just a general discrete probability distribution. It's not of a particular type. It's just we've got some values that X could take on, and we've got the probability that X would be those values. So what would be helpful, though, is if this was a particular type, it would be helpful to kind of think through what type is it. And really, the only other one that we know about at this point is this idea of a binomial distribution. So if you remember from talking about the formulas, binomial is nice because it has an easy formula to calculate the mean and an easy formula to calculate standard deviation, and not necessarily easy, but a straightforward formula for calculating probabilities. So to figure out if this is binomial, you just have to spend a second to say, are there a fixed number of trials? Yes, there's 6 seeds that are planted. Are there 2 possible outcomes for each of those 6 seeds? Is there a success and a failure? Sure, they either grow or they don't grow. Are they independent? So one seed growing, does that affect the probability others are growing? No, so these are independent, so that checks out. You need those 3 things. And then does that probability of success, is that the same for each of the 6 seeds? And yeah, they each have a 75% chance of growing. So it checks the 4 boxes for being binomial, which means we can use what we know about binomial to calculate either the mean, standard deviation, or in this case, it wants to know what's the probability of 3. So if you have to calculate a specific probability like that, then you're going to the formula sheet. Come on. There we go. And you're using the binomial probability formula, which will be this one. So n is the number of seeds, x is the number that you want to grow into healthy adults, p is the probability of growing, and then q would be the probability of not growing. So
Okay.
this, you just have to keep in mind, that's your binomial probability formula. So if you have a question like this where it's binomial, then use that formula. Or it might be asking for the mean, or it might be asking for the standard deviation, but those all have easy formulas with them. So,
Okay, so if for that one with the exactly 3 don't grow,
yeah.
The x would be 3?
Well, yeah, it's good. This one's tricky, and I won't be this tricky on the exam. But so if you think of a seed growing as being a success, then 3 not growing, that would be 3 failures. But since there's 6 seeds, if there's 3 failures, that means there's 3 successes. So yeah, 3 would be x.
Okay.
Good.
So like the number that they say.
Yeah. So in general, you can assume that this smaller number is going to be your x. The bigger number will be the n. And then if they give you a percentage or a proportion or some decimal value, that's going to be your probability of success, your p.
Okay, that makes sense.
So, but check for that. If it doesn't say normally distributed or uniformly distributed, check to see if it meets those criteria for binomial. Number 6, it doesn't. So you kind of have to calculate these. Basically, the problem with number 6 is the trials are not independent. Once you get a success, that affects the probability that the next one's going to be a success. So those are not independent. And so you have to build these probabilities out using what we know about. I think this one uses the multiplication rule and whatnot. So try it. Try number 6, but just realize number 6 is not a binomial situation.
Okay.
All right. Number 7, you're playing 1,294 games. The probability of success is 0.85. And so this one turns out to be a binomial. It meets those criteria, but I'll let you check that. It wants the standard deviation. And so now you can use the standard deviation formula for binomials. And that's the really easy one where it's just the square root of n times p times q. Right. Oh, and this, I should point out, this is the most likely number of wins is a way of asking for the mean. So part A, you can use the easy binomial mean formula.
Oh, okay.
But once you realize it's binomial, forget about all the other formulas, and there's just the easy mean, the easy standard deviation, and then that kind of more complicated probability formula.
Got you.
All
Okay.
right. So I don't know. I would say that's probably a good start as far as what to look for a good chunk of these problems. But you know, spend some more time studying.
Yeah.
When are you guys planning on taking the exam?
I don't know. I was maybe thinking about taking it tomorrow, or it's due on Wednesday, so
Yeah.
maybe Wednesday morning before class, or Tuesday afternoonish. But yeah.
Okay. All right. Good. Yeah. So
Yeah,
take some more time and study then.
Yeah.
I might turn it in a second before it's due, but we'll be in.
Do that too. I don't recommend it, but you can do it.
Have to learn the hard way somehow.
All right, guys.
Thank you so much.
That was very helpful.
Yeah, good. I hope so. But yeah, study.
Yeah. Okay.
All right.
Thank you.
Good luck.
Thank you.
All right, bye, guys.
Bye.